Okay, the first thing is, so I have already posted the recorded session on the YouTube, so you can through the Blackboard link to check. If you're missing some portion of the class or you want to review the portion of class, you can look at the YouTube and see what happens. So today we will continue our assembler, and I will also do some demo to see for the CPU emulator. So for CPU emulator, you will do is, okay, I will upload my assembly language symbolic version, and then it will do directly convert to the hack machine code. So it's like a machine code, so it's binary representation. And then you will have another homework. So I think this is the last homework. This one is deal with the assembly language. So you write the assembly and convert to the machine code and run your code and see the results. So make sure that the deadline for the homework is April 10th. But April 10th is the university holiday, so you just need to send me email through the course mail to submit your homework. So take the screen. In this class, I will show which screen I want to see so that you can take the screenshot and send it through the course mail. Okay, so far so good. Any questions? Okay, so now I will share the screen. Oh, last class we do assembler. So everyone can see the screen? Okay, so let us see. So in this screen, I use a sample code we learned in previously is add from 1 to RAM 0. So RAM 0 is actually the number provided. For example, here I do is to 100, it's okay. So what we will do for this one assembler. So last class we deal with, okay, how do we deal with A instruction and how do we do the C instruction? This one is provided by assembler. It's automatically can convert C instruction quite easy, just like a table lookup. And then if I have the A instruction, if I give you the number, for example, I give you 100, definitely you can convert this 100 to the binary representation. But if I give you is the variable, so for example, in here, I give you at I, so how do I do that? Okay, we say that, okay, I should create a symbol table so that I can convert the variable to the number, right? So this is one thing. If you have at I at summation looks like that. And another thing is if I have the control stuff, so like the loop or write, this kind of thing here or and. So this one is actually I need to count the number of lines, the lines after this number. Okay, so today we will go over it a little bit to see that how assembler deal with assembly language. So, okay, so the first thing assembler will do is, okay, when you give me a symbolic version of code look like this, it will first create a symbol, which is the predefined symbol. So this predefined symbol include 16 registers from 0 to 15. Okay, so this one is the first predefined symbol. And then you have another two predefined symbol, is one for screen for output and one for keyboard as an input. So this two, the starting address is showing at here. So this one is the RAM address, right? So this one is showing here. What else? So this is also predefined symbol. So this predefined symbol, this one, oh, let me see, I will use pen. So this 5 from 0 to 4, this 5 is our is for the virtual machine usage, which is already overlap with this 16. So you can see that SP is 0, local is 1, so argument is 2, so it looks like 0, 1, 2, so it's a memory address from R0 to R4. So actually you have 5 registers. This one we will discuss a little bit later in the virtual machine. This one is very, very useful for the virtual machine to deal with the high-level language. This high-level language, actually, you will see that, okay, in our high-level language, it's not like assembly language. You don't have methods or functions provided by assembly language. But in your high level, you will have assembly, you will have high level language to deal with the methods. So the methods, you will have local variable, you will have passing variables. So this is argument is passing variables, and local variables declared by the method itself within the method itself. So this one is quite useful, but here our assembly language do not deal with this portion. That's why we don't discuss it here. Okay, now the next portion is assembly language will do the first pass. So this one is already created in the symbol table. Then the assembler will do the first pass. What is the first pass? Is to create, okay, this is line 0, this is line 1, this is line 2, then this is line 3. Then, okay, so this is the label, right? The loop is the label. Actually, it's no meaning to machine code. So if I have the label here, so I will replace the label by the line of the code. So here I have the label loop. The first line after the loop, the line number is 4. So the loop will be represented by 4. Okay, then I have 5, 6, 7, 8, 9, 8, 9. This is 9, 10, 11, 12. I don't write the number, but just a count. 13, 14, 15, 16, 17. So I meet another label called write, right? So the next line after the write is 18. So I will write, okay, in my symbol table, I will write write. Okay, this is the write. Right. Okay, this is right. I will write, okay, this number is 18. Okay, so for this one is 18. Okay, so 18, 19, 20, 21, 22. So end, after the end is 22. Okay, so I will record the end in my table. So this end I will write is the number is 22. Okay, so this is, we call it the first pass. So first pass. First pass. First pass. Okay, so the first pass, actually the major things is try to set up the symbol table, which is, okay, I have the label usually right at the uppercase letter. So this is the label. So I see one label. So if I see one label, then I will say that, okay, this is what is the line for those label. So I will write n. So I will insert into the symbolic table with this two values into the symbol table. So what is the label, what is the number? So in this example, we have already seen, I will write this 3 into my label. Symbol table. So one is loop, one is right, one is and. Okay, this is the corresponding number. So actually is the first line after this label. Okay, so this one is our first pass. Okay, now when the assembler finishes this first pass, it will go to the second pass. Okay, so the second pass. Second pass is actually the translation pass. Okay, so this is the translation procedure. So now the second pass, it will first look at, okay, if this is A instruction with the exactly number, I will convert it directly. If it's a C instruction, I will look at the table to create my 16-bit C instruction machine code. But if I see the variable, so see this one, say here in this example, I see at I. Now I will look at the table. So the table may give me two things feedback. One is to say that, okay, this one has already record. So I use R, record. So record, RD, record. If it's already record, then it's quite easy for me to just use the label, recorded the label to there. So what is the record, for example, at here, at R0, right? This one I have already put in my symbol table. So if you get R0, it will directly replace R0 by 0. So it will be at 0, right? So it will be at 0. Then since it's at 0, then I will do is, okay, 0, I will convert to the binary representation. So I give you 16 zeros for that line. So this one has already been recorded. So you may also have certain case which is not record. So not record. So not RD, so not record. If this one is not recorded, then what I will do is, okay, I will do is check the first available RAM place. So the RAM from 0 to 15 has already been recorded, so already used. So this one, so the first available is 16. So I will have 16 as its number. And I will, similar like the first pass, I will insert this new values, new entry to the symbol table, because it's not recorded. Now this time I is replaced by 16. Then I can convert to 1 0 0 0 0, right? So this is 16. Then put it into 16-bit. So the total length. So I don't write too much. So I will put multiple zeros before that. And this one will be the 16-bit representation. So similar to the summation, if I move to summation here, so the summation here is not recorded in the symbol table. So I will create summation in the symbol table and put 17 as its address. So because this is the first available address. So this is 17. And when I write it, I will replace by 17. So this one will be 10001, right? So then before that, I will put multiple zeros and make it to be 16 bits, totally 16 bits. Okay, so then I record it into the symbol table as my second pass. Okay, I can move forward if I come to this at I again, since I is already recorded, so it will follow here. So it will be recorded and put 16 replace I here. You will not create the new memory address because it's already recorded. Okay, so then everything is the second part. So you look at associated with the symbol table. You will convert each line to the binary representation. This is the machine code. So assembler will be, okay, so okay. So this symbol table is generated by the assembler. So based on this loop, this kind of thing, make sure that this slide has one thing missing is the loop, right? Loop is 4. So, and used to translate the symbolic code into the binary code. And in general speaking, so this one you have the initialize. The initialize is create an empty symbol table and populate it with a predefined symbol. So it's from R0 to Z in this case, in this example. And then our first pass will generate all user-defined label, control label. So we have the loop and the white and the end, these 3 things, and put into the symbol table. And the second part will go again to the source code and convert your source code to the binary with some variables you are not recorded in the symbol table. So you will add variables and give the first available RAM address to that variable. Okay, so far so good. Okay, seems easy. And okay, so today I will show certain kind, I will show the summation as an example. I will stop sharing. So here, this is I start my simulation. So show the example and which you will be used in your homework. So here, previously you will use a hardware simulator. And today we will use the CPU emulator. So same as you start the hardware simulator, but you just use the CPU emulator. So when it's start, it looks like this. So I will share another screen. So this is the screen you will see on your computer. So this is the CPU emulator. Okay, so when you, yes, so any questions? Oh, you can't see that? So I will stop for a while and then restart again. Okay, so now this one is your emulator interface, okay? And then you will load the program, similar like your hardware stuff. So you should write the program before you load it. So you can use any word editor or whatever. So write your assembly symbolic version code. So this one is I write. So symbolic version code. So of course I can do this is at I at summation. So, but you can also, if you load it and you want to change, it's fine. So you can change inside. So, but when you run it, it's assembly language, it will do it directly. So it will convert, it has already converted to the numbers. So it's not assembly here. So, but I will see, so let me see, stop sharing. Yeah, it's a little bit headache. So this one is my code. So this is my summation from 1 to 10. So not 100. So 1 to 10. So I write at I am equal to 1 at summation, m equal to 0. I have the loop similar to similar to the slice from add from 1 to 100. And then this is the end, right? So I have loop and end. So this is 2. So when you finish writing assembly language, so this one, you should put in your submission homework. Okay, so when you submit your homework, the first file you should submit is your assembly code. What is on this screen? You can store it in the TXT file format, so it's fine. So when you this is the assembly. When you finish, you save it, and when you submit the homework, you should submit this one as the first file. So this is my assembly. So I don't want to go over it because you have already familiar with this one to add from 1 to 100. So I just make it to 10. Like this is just a little bit of change. Okay, so this one is, I can put a little bit, if you want to change, you can put a little bit is at, I can do at R0, m equals to 10, so that I can do, this guy is m equal to 10. It means I put the 0, 10 there. So I am equal to 1 and 10 at I. So at R0, so if it's R0, A equal to M, this means I get 10 from the memory. And then D equals to D minus A, then I will convert. So at I will D equal to M and summation and let I increase by 1. So this is I store. So if I do these things, then I can change my M, right? It's more flexible. So I can change the value stored in M. You can store 10, you can store 100. So when you finish, so I can save it. Okay, so this time, oh, let me see. Oh, if I start, then I go back to my CPU emulator and reload it. To reload? No, not yet. So let me see. Oh. What happens? It's not loaded. Okay, I will restart. Okay, wait a moment. I will fix my, or maybe I will say, okay, so let me see how that I can load it or not load it. So maybe I will come back. Okay, so okay, so I will come back a little bit. Oh. Okay, so let me do this. Okay, so and let me come back. So share screen. Okay, so when you store your assembly code, then when you load it to your systems, then you will see that your actually all your variables has already replaced by the add stuff. So it's already replaced by the number. You see the black screen? Yeah, I think it's a kind of problem. Can you see now? Okay. Yeah, this is kind of the province. My computer is now it's crazy. Okay, so this is assembly language, but it's a little bit crazy that this one has already replaced all the variables by the number. Also, if you want to jump, it's already replaced by the line number. So this one you cannot see anything with the variable. So that's why at your first submission, you should give me your assembly code so that I can see what variable you use and what kind of control you will jump. So instead of I just say at 18, so at 18 here, so it's you jump to here. So it's a little bit headache to indicate. Okay, when you finish this assembly, and load it into your CPU emulator, then you can see the binary. If in the ROM part, you have two memory, right? One is ROM for the code and one is RAM for the data. So you will see that this ROM, if you click binary, you can see it's already converted to the machine code. Even if you don't convert it directly, it will convert for you. So, but when you submit your code, your screen, the second part you should submit it. The sub is the screenshot on this screen. So you should see. You should let me see your assembly code loaded to the CPU emulator, and then the third screen. So the second screenshot, this is the first screenshot, right? Your first file should be your assembly file. Your first screenshot should be this, you have already seen. And the second screenshot should be the binary, okay? This is the binary. Okay, then you can click run here. If you want to run one by one, you can run here. So this is one step by one step. It looks like this. So you click it. So you will see that there is information changed at the RAM place, right? So you can go on, and then it will do calculation. You will also see the ALU output here. So I don't want to see that many screenshots, but you can click run here to let it run. So you will see that the ALU will run, and the A register information, this is your counter of the program. So which line you are running, and this is the output, the ALU output and the ALU input, whether it goes to the D register or it use A register or M from the memory. So it will run for a while. So let us see for a while. That's why it will take a time if I do 1 plus 2 to 100. So this time I just 1 plus 2 to 10. So you can see what happens. So you can see the ALU, it will run the code. Inside the ALU, this is the code it runs. So which computation it do. Here is D, it get the D. So it get M value, it do D plus M. Now M increased by 1. So set to 0. Okay, M. So this is what they do. And the D register is also shown here in the D register. So you have A register here, you have D register here, and the PC is the program counter. ALU will do automatically based on your code. Oh, continue run. If I click here, so it will stop for a while. So you can stop for a while, then let it run. So finally, your D input will be 10, and when it go to 11, it will be positive and stop my code. Oh, this is the whole procedure, and then now this time D is equal to 10. So when you go to 11, you minus, you get the positive values, it will stop. Actually, you will see that your code will not actually stop. It's just do the infinity loop between line 18 and 19. You can see your assembly code. You can see your assembly code is say 18 and 0 jump, right? So actually it will not stop. It's just do the infinity loop at here, but no change of ALU, no change of the output, no change of all this A and D values except the program counter. Okay, except the program counter. So this is the whole thing for the running. And when you finish running, you will see that your summation value is stored at RAM 17 because your summation, the first available memory address for summation is 17. So it will store your final value at here. So your final value will be 55. So this is the whole thing, the whole demo. So when you finish your homework, you should give me the last screenshot is show your results. So your production, I hope you will show it on your screen. So it will show your results at here, not at the RAM place. So you will see your RAM place is very large. So if you don't go to, if you use the screen, you should use the memory at this screen memory. So you write to the screen. It will show on the screen. Okay, so far so good. Okay, so this is the simple demo for the summation, and your homework will do the production. So you will ask the customer, so you can type in 2 values. So at the beginning, for testing purpose, you can just hard code your 2 numbers. Don't that big, so don't do 1,000 times 2,000. It will be ridiculous, too big. Okay, you just do 3 times 4 like this, so you can see what happens. Since our hack machine does not support multiplication directly, so you should write the code to add the multiplicand multiple times, right? If you 3 times 4, it means that you will do actually 3 plus 3 plus 3 plus 3, so actually 4 times. So this is your output, okay? This is a little bit crazy, but it's doable. Any question? Okay, so we finish our assembler, and your homework, I do the demo and give you the hint of what kind of screenshot I want to see and what is you should also provide the assembly code there. And you should also deal with the keyboard and the screen. So let customer use keyboard. Keyboard is here. Keyboard is here. You can type in values there. So it looks like this and 3, 4. So it's keyboard here. The big white here, the big white portion is the screen. So view screen, you can view script. So you can view output, you can, here, your view is the screen. Here is the screen. Okay, so this is the whole stuff. And go back to our slides, and the last things I need to discuss is for the operation. So I have 2 groups will do assembler. So this is a good thing for you to understand. So this is briefly summary. So you have initialize first parse and the second parse. So what it will do, so A instruction, C instruction is simple. You just replace and you have symbol. You will have 2 possibilities. One is you found that symbol in your table, so you directly use the numerical value. Otherwise, you will insert a new entry into the symbol table. So this is the whole things for implementation. And for this software, actually, they implement and give us the simulator. So your group project 1, guys who will do the group project 1, you will do it by yourself. So this is a good reference for you to look at what is the implementation inside here. So you have the parser. Actually, the most complicated thing is the parser part. You have the command type. You have A command, C command. So in this place, so A command, C command, and L command. Right, L command is actually deal with the symbol. Right, so if you do your assembler by yourself in group project 1, you should deal with this error command. Okay, and then you have, this one is for C instructions. You have destination, computation, and the jump, right? So this one is just for C instruction. And what is the output? Okay, so this is the implementation for our assembler. And if you do group check project 1, so this is a good reference here. You should look at their reference. Any questions? Let me see. That's all for today's class, and you can talk with your group member to check the progress of your project. So everyone got the assignment for the group project and also know the group member. So you can talk with your group member to discuss and separate the task between you and your group member. So if you have any questions, I'm still be here to 11:35 to the end of the class, so you can ask. Okay, if you don't have any questions, then see you next week. If you have, you can ask.